Okay, everyone. I think we left on question 13, and question 13. My UU has applied to both Harvard and the University of Florida. She thinks that the probability that Harvard will admit her is 0.4. I think she needs to reconsider that. The probability that Florida will admit her is 0.5. She definitely needs to reconsider the 0.4 if it's only 50% of Florida, right? Okay, the probability that both of them will admit her is 0.2. So what I've done here is I've filled out two Venn diagrams. The first one that you see here is a traditional Venn diagram, which are certainly welcome to use if we had used... Sorry. You're certainly welcome to use the traditional Venn diagram, but I don't particularly think that it's as helpful as a modified Venn diagram or the probability chart. So in the Venn diagram I've labeled these. Okay, the left circle is a probability of getting into Harvard. The right circle is a probability of getting into Florida. The almond shape in the middle, that's a probability of getting admitted into both Harvard and Florida. And whenever I fill these out, I always wait to put any numbers in it until I see an intersection, because that is going to be the really big determining factor. Yeah, that's going to be the big determining factor here, is what is this common ground here. So as soon as we read that the probability that both of them are going to admit Mayu into Harvard and Florida is 0.2, that allows us to fill out the rest of the chart. So if we know Harvard is at 40%, the probability of Harvard and not Florida is 0.2. The probability of Florida and not Harvard is 0.3. And if we take a look, we have created 4 disjoint regions. Number 1, number 2, number 3, and then the outside is number 4. So the probability of not being admitted into either college is 0.3. Okay, that's perfectly fine. I do, however, suggest that you use the modified chart, which looks like a probability chart. It is a probability chart. It doesn't look like a probability chart. So again, in the probability chart, you want to write down the total probabilities at the bottom. So here it's easy to write this. 0.4 is the probability of getting admitted into Harvard. Hi, Steering.
From the CA.
Oh. Please fill out. Oh, okay. Yeah, thank you. Pia Del Monte. Okay. The first row is a probability that Mayu gets into Florida. That's 50%. After you have those 50%, it's easy to fill out the rest of the sides because the sides need to add up to 1. So it's 50% she can get into Florida, 50% she's going to be rejected from Florida, 40% that she's going to get into Harvard, 60% she's going to be rejected from Harvard.
We still have to come back to you if you can volunteer for skate night. December 2nd.
December 2nd.
6:30 to 9:30.
Is this your event? Is it your event?
Yeah.
Ooh. Boston Bruins are in town.
I think you could do it.
Yeah, put me down.
Yeah? Okay.
Yes, he is. And if it's you? Yes, this is. What?
Hey. Yeah, here. corridor. Yeah, sure. Buddy. Buddy.
Whoa.
Whoa, special phone call for
It's the
Claudia.
AD.
It's what?
It's the AD.
Hello? Hi.
It's the AD.
I am.
Athletic director.
No, I turned in my,
She's getting sassy with them too.
yeah, I haven't been able to get my physical done. I'm getting it done this Friday.
What'd you have? What'd you have?
I had salmon and salad, but I gave my salad to Connie, and I stole some of mine.
Am I gonna be able to do it though? Okay.
There's always
Yeah.
different menus.
No, yeah, I didn't go.
Yeah.
I didn't go today.
Okay, let's finish this up, everybody.
Yeah.
Okay, once I've figured that out, again, just like in the traditional Venn diagram, I do want to start with the intersection if I have an intersection. So the intersection here of Harvard and Florida is 0.2. I think this will be really nice for you because I'm also labeling this with what each intersection is. So this is Harvard and Florida. This is Florida and not Harvard. Harvard and not Florida. This is not Harvard and not Florida. Once I have that 0.2, I can use properties of addition and subtraction to get the rest of the numbers. So 0.2 plus 0.3 is 0.5. 0.2 plus 0.2 equals 0.4. 0.3 plus 0.3 is equal to 0.6. And of course, 0.2 plus 0.3 should have been equal to 0.5. At this point, we can also say something interesting. We can also figure out whether or not the probability of getting into Harvard and getting into Florida, we can figure out if those are independent or not. Let's multiply. What's 0.2 times 0.4?
0.8, right? 0.08.
I'm totally wrong. 0.5 times 0.4. 0.2, good. Notice how this works as an addition, as a multiplication table. 0.5 times 0.4 is 0.2. 0.5 times 0.6 is 0.3. 0.5 times 0.4 is 0.2. 0.5 times 0.6 is 0.3. All the multiplication works, right? If all the multiplication works, then the two events are independent. That's not asked for in this, but it's certainly worth knowing that you're looking at a chart of independent events. Sarah, did you have a question?
Yeah, I get the probability chart, I just don't get the Venn diagram. Like, I don't get
It's okay. The probability chart's better.
so, but like it asks like make a Venn diagram.
You can use the probability chart for the Venn diagram.
You can?
Yeah.
And what did you say? You said if all the math.
If all the multiplication works out, then you have independent events.
Which multiplication?
In this case, it'd be the side, 0.5 times 3.
Whoa. Oh god.
In this case, it's 0.5 times 0.4 is 0.2.
Uh-huh.
0.5 times 0.6 is 0.3. 0.5 times 0.2 is
Oh.
0.5 times 0.3 times 0.6 is 0.3. So it kind of works like a multiplication table. Yeah, they are independent if the multiplication works out. All right. Any other questions? This is good questions. Good questions. Redundant, but good.
I have another question.
Sure.
Okay. Wait. Okay, so if you, like, why isn't, okay, I feel like this is a really stupid question, but why isn't if you multiply the probability of H and the probability of F, that would be the H and F?
Yeah. It should be in independent.
Uh-huh.
If H and F are independent, then that multiplication will work out. And that's what we did here. The probability of F is 0.5.
Uh-huh.
The probability of H is 0.4.
Oh wait, yeah, just kidding. So it is. Okay, no, sorry. I was looking at 3 and 2, and I was like, why isn't that 0.06? But never mind. Yeah.
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 Okay. Once we have those charts, the rest of these questions fall out pretty easily. we have our Venn diagram again. You're welcome to use a probability chart instead of the Venn diagram. I would actually recommend that you use the probability chart and not the Venn diagram, because then you can answer all sorts of fun questions like letter B. What's the probability that neither university admits her? 0.3 is not Harvard and not Florida is 0.3. Letter C. What's the probability that she gets into Florida but not Harvard? Florida and not Harvard. 0.3. 0.3. Okay. You could also ask wonderful questions like, what's the probability that she gets into Florida if we know that Harvard rejected her?
Oh, that's sad.
It's a little hard.
It's kind of expected.
Taking notes is troubling.
0.5. It's Florida and Harvard complement divided by Harvard complement. But because they're independent, it's definitely 0.5.
So wait, what?
Should I write that for you?
Yeah.
Oh, we have it right here. What's the probability that she gets admitted into Florida if she was rejected from Harvard?
Oh yeah, that makes
That's the probability that she got into Florida and not Harvard, divided by the probability she got rejected from Harvard.
Should we write down that notation before we do 0.3 divided by 0.6?
It'd be good.
Okay, it'd be good.
It would be good to do. Any questions? And then, like we were saying, that because they're independent, the probability of Florida and not Harvard is still going to be 0.5. Still going to be the same as the probability of Florida
Oh.
because they're independent. So much here, yeah.
I know you were talking about like a few days ago about the traffic light and they're not, they're dependent. Can you explain how they're dependent again? Like the traffic light.
Can we do that when we're off
Yeah.
cam?
Yeah.
Where'd I get it from?
Let's go to 14. This is a fun one. Okay, if you can get if you understand these problems, you're doing really well with probability. Because I tell you what, most people will not be able to get this question right if you just ask randomly. Okay?
Oh no.
Heart disease is the #1 killer today. Suppose that 8% of patients in a small town are known to have heart disease. That seems like a really low number. It's a really healthy town. Okay, suppose that there's a test that is positive for heart disease in 96% of patients, but is also positive for 7% of patients who do not have heart disease. Okay. All right, that's all the information we need to actually fill in this chart. So the first piece of information that we're going to look for is something where the two events are not mixed up. And that was actually the first clue given to you. 8% of all people in this small town have heart disease. So if you look over here, we have H equals heart disease. Plus means the test is positive. Negative means the test is negative. The probability of heart disease, not Harvard, heart disease, going down over here is 0.08. Probability of not heart disease, this is all 2 for 1. If we know the probability of heart disease is 0.08, the probability of not having heart disease is 0.92. Okay, next clue. Wait.
Is that 92 for part that they don't have heart?
Yes.
Why would it be 92?
8% plus 92% is equal to 100%, yeah. Okay, next, 96% of the patients who have heart disease are going to test positive. Which is like saying 96% of this 8% will test positive. 96% of 8%, that is 0.0768. Also, 7% of the people who do not have heart disease will also test positive. 70% of 92% will also be positive. 7% of 92% was 0.0644. Once you have those numbers, you can use addition and subtraction, mainly subtraction, in order to get the rest of the probabilities. For example, these two boxes have to add up to the probability of heart disease. So this box here is just 8% minus 0.0768. That gives you 0.0032. This box over here, this one plus this box has to equal the probability of not having heart disease. So 92% minus the 0.0644% gives you the probability that someone is randomly chosen person, does not have heart disease, and they test negative. After all four boxes are filled in, we can add across to get the probability that a randomly selected person will test positive. 0.768 plus 0.644 is 1412. Okay. We have two ways of getting this one now. We could either add across, or we could subtract from 1. Either one should get you the same number, and if they don't, you made a mistake. Okay. That's all the information you're going to need to know. Additionally, right now you can probably tell whether or not the events of whether the heart disease and testing positive, whether or not they're independent. Not independent in the English sense of the word, independent in the mathematical sense of the word. So, is 0.1412 times 0.08 equal to 0.0768? Definitely not. Multiplication doesn't work, therefore these two events are not independent. They are dependent. That is. Multiplication doesn't work in this chart. So the two events, heart disease and test outcome, are dependent. Okay. And I think we're ready to answer some questions, right? You want answers? I want the truth. You can't handle the truth. I only saw that movie once, but that soundbite gets replayed pretty often. Soundbite. You can't handle the truth. Jack Nicholson, yeah. Tom Cruise, Jack Nicholson, that's right. Tom and Jack. What's the name of that movie? A Few Good Men. Thank you. A Few Good Men. It's all about Guantanamo. America's dirty secret. The dark underbelly of democracy. It's awesome. My pen doesn't work. Give me a moment. Death Note.
You rename it Death Note?
I did. I thought I did that in this class. Maybe it was 5th period. Death Note. Previous session. This would be a lot faster if I wasn't streaming. It's okay. Nothing to apologize for. It is what it is. And what it is slow. Part A. Part A. If a person is selected at random, what's the probability that that person has heart disease and tests positive? Heart disease and tests positive. Notice that it said a randomly selected person. We know nothing about them other than that they're in this small town. So we can read that from the chart. At the top left box is 0.0768. Letter B. What's the probability that a randomly selected person does not have heart disease but tests positive anyways? Probability that someone does not have heart disease, that's H complement, but tests positive anyways. Oh, poor guy.
What do you mean? He doesn't have heart disease.
0644.
But he thinks he does.
It's a lot worse to get negative than have it.
It's true, there's definitely worse. I mean, this person's gonna come out a lot healthier in the end of it.
Yeah.
Already doesn't have heart disease, but then he's gonna start like eating vegetables and going jogging twice a week. So. I think C is the one is the hard one. Oh no, it's not.
No, C's kind of.
The probability that somebody tests positive, okay? So remember, if it's only one event, we're not doing an and, we're not doing a conditional. We only have to look we have to look at the margin. So this probability that someone tests positive is 1412. 1412. I feel like 1412 is one of those dates that I'm supposed to memorize. Anything happened in 1412? Probably.
14, 12?
14. I remember 1412. Well, something happened.
Nothing significant happened.
I bet that someone in the Catholic Church was bribed. That's always a good bet. Letter D. If someone tests positive, what's the probability that they have heart disease? All right. So do we know that they have heart disease, or do we know that they tested positive? Yeah, we know they tested positive, so we're going to put positive at the second half of that conditional. So basically this says, what's the probability that someone has heart disease given the fact that they were tested positive?
96%.
Okay. So that is the probability that they tested, that they have heart disease and they tested positive, divided by the probability that they tested positive.
Isn't this already given to you?
No.
It's not 96%.
That's the other thing. 96% is...
Oh, give me the heart disease. Right.
Mr. Perry, I have a question. If they ask you if it's independent or dependent, but they say why?
Because the probability of positive and heart disease is not equal to the probability of positive times probability of heart disease.
Okay, so
Let's do that in a second, okay?
Okay.
That's actually really good.
wow, I asked good questions.
All right.
Not Florida.
Not Florida. Nothing against Florida. What was the probability of testing positive? 1412. It's okay. That's somewhere near 50%. What was it?
5, 4.
And look what that says. If you tested positive, you only have a 54% chance of actually having heart disease.
That's pretty
That's not that good of a test, right?
But it's a good motivator.
It's a good motivator, yeah. You'll come out healthier.
It's a good motivator if it says you have a positive.
Like the way I can just put myself
I
down.
think the scary box, the box that you don't want to be in is this one right here.
Ooh.
You tested negative. but you actually have heart
So you can
disease.
eat as much bacon as you want.
Yeah, that means you keep on with your bacon eating ways, but you have heart disease. This is this one over here is bad, but not quite as bad as this one right
The
here.
chances that that one is pretty slim though. It's 0.32.
Yeah, you're right. That's probability being this box is pretty small.
The other one is actually not bad. I don't think so. No.
This one?
Yeah.
You don't think it's bad at all?
No. You don't have heart disease.
Okay, so the extension question, I think this is probably where we're going to have to leave off. I don't know. Maybe we can do another one. The extension here is R H and positive independent. Okay. And remember, we had two ways of doing this. Number one, the first way we learned is if the probability of H and plus is equal to the probability of H, then that would mean independent. Okay. We already computed this as 0.5439. We already know that the probability of having heart disease is 0.08. Not equal, therefore not independent. That's one way of doing this. The second way of doing this is if the probability of H and positive equals the probability of H times the probability of positive, then that would be independent. Probability of H and plus, that was 0.5439.
No.
No.
No. HN plus was point oh seven six eight, I think.
0768.
Yeah.
Is that equal to 0.08 times 0.1412?
I don't think.
I don't believe it is. Therefore, not independent. Okay. So two ways of showing independence. 5% of my battery left. I put my charger on a timer, that way I'm not going to overcharge my battery. When it's 100%, you just keep charging.
It ruins it, right?
It ruins your battery.
Where's the timer on your phone?
They do that every night because I sleep.
I know. You need to buy a timer.
I don't have money for that, so I just overcharge.
$10. $10 and your battery will last longer.
Do you have a timer on your phone?
Wait, what do you have?
I should have seen
Yeah, I'm not gonna wake up in the middle of the night when
Make yourself
Wait,
wait.
I have a timer.
Wait, what do you put on your, what did you buy for $10 that helps your battery?
A timer. You know the kind of timer that you use for like Halloween lights or Christmas lights or whatever? You buy one of those timers, plug your charger into it, you're good.
So kind of like shuts it off.
Mm-hmm.
Oh, it doesn't?
Yeah.
Can you explain again the second way of telling us?
Sure. The probability of the intersection, if it's equal to the probabilities multiplied, then you get independence. Okay. We already computed the intersection to be 0.0768. We know that the probability of heart disease is 0.08. We know the probability of positive is 1412. These two definitely are not going to multiply to make that.
Okay, thank you.
And I think we're going to have to stop it here then. And here's I need everyone's attention for this.